In this video, I want to sort of round up some of the things that we've discussed in the past and introduce another twist and turn in the nature of stationary point and point of inflection work. So at the moment, we know that whether it's a local max or a local min or a point of inflection like that or a point of inflection like that, we know that for stationary points, dy by dx equals naught, and that's something that you need to know off by heart. We also know from year 12 that if you work out dy by dx squared for the stationary point concerned, whether it's one of those, this one, or this one, that if you get an answer to be positive, then it would be a local minimum. So we'd have that scenario. And that is something you can learn off by heart and use to identify a local minimum. If when you work out the second derivative it's negative, then it is a local max, definitely that situation. But I showed you in the last video, sometimes you might find that it's equal to naught, and when it's equal to naught, not anymore is it the case it's automatically a point of inflection. I showed you in a previous video that this is an ambiguous case, and it could be either a local max, a local min, or a point of inflection. So if it's going to be a point of inflection, it must be true that d2y by dx squared equals naught. That must be true. But generally speaking, if you do that and you get equals naught, you need further work with the gradient method in the region, in the neighbourhood of the point of inflection to decide, like I showed you in the last video, whether it's a max or a min or a point of inflection. Now, however, I need you to understand that if you have d2y by dx squared and put it equal to naught, if there are any points of inflection, then you can find those points of inflection, by saying let's work out d2y by dx squared and putting it equal to naught. Because if it's a point of inflection, it definitely will obey that condition for this scenario. Points of inflection always must have d2y by dx squared equals naught. Even though, as I've shown you, that it's an ambiguous situation. It's only the situation which gives points of inflection. Right, now, just to throw a spanner in the works even more, you can see these are points of inflection which are stationary points. But there are points of inflection which may not be stationary points, because you could have a curve doing this sort of thing, swinging round and then doing that. And so what you've got is it swings round, but that at that point there, which is a point of inflection, you do not have a stationary point because the gradient isn't zero. The tangent isn't a flat line. The gradient goes from being positive one side of the stationary point, sorry, one side of the inflection point, and then on the other side it's also positive. So it's going positive, and then you've got positive on the other side, but you do not have zero in the middle, because zero it's not a flat line. The gradient isn't a flat line at that point. So some inflection points are not stationary points. They're just inflection points which are doing that, or possibly the other way. They may be going like that. So we've got an added complication for inflection points. So in a nutshell, inflection points, it will be true for all inflection points that d2y by dx squared must be equal to naught for inflection points. Got to be. If d2y by dx squared is positive, it's a local min. If it's negative, it's a local max. So d2y by dx squared has got to be naught for inflection points. Okay? But, and here's the thing, they don't have to be stationary points. So when you work out dy by dx for something and you get some stationary points, it may be that one's a local max and one's a local min, and another one might be a local max if you've got three of them. And you might say, oh, it's got no inflection points at all. But what you might find is that this particular curve does have a point of inflection which is not a stationary point. So for example, I'll give you a little sketch. You might have the curve looking like this. Like that. It's got a stationary point there, a stationary point there. So if you did dy by dx equals naught for this particular curve, you'd find two x values where you've got zero slopes. And one would identify as a min and one would identify from a max from this method. However, it does have two inflection points. One inflection point is there and one inflection point is just here. And these inflection points would not be a stationary point, so you wouldn't find them coming out from that equation. What you'd need to do to find these inflection points is you'd work out d2y by dx squared equal, and put it equal to 0 for inflection points, and that equation there will work out for you all the values where you have d2y by dx squared equals 0, which will give you inflection points even if they are not stationary points. So this here and this here would be identified from that equation, and they don't necessarily have to be, and in fact they're not in that picture, stationary points. Now I hope I haven't confused you with all this information here. I'll in the next video show you with an example to show you how it works and show you it's not as confusing as it might first appear.